Work a kinematics problem in the vertical direction. So it's a free fall type problem because we're going to ignore air resistance. So kinematic equations in the vertical direction. We have a helicopter. Imagine a helicopter moving upward, straight upward at 22 meters per second. And we've got a dense rubber ball, mass of 0.4 kilograms. The helicopter door is a design where the doorway is open, and somebody rolls the ball out of the doorway. It's moving at 5 meters per second. The ball is in the horizontal direction as it goes out the doorway. At this time, the helicopter is 230 meters above the ground. I want you to calculate, I want you to watch me calculate, I want you to calculate what's the maximum height for the ball. So we have this helicopter, and crude drawings are all I can do here, but the ball comes out here 5 meters per second. The helicopter, and where the ball is 230 meters above the ground, and the helicopter and ball together are moving upward at 22 meters per second. I'm going to work this problem with positive being the upward direction. We're talking about ground, talking about helicopters, so there will be a vertical acceleration in the problem, and that's provided by gravity. So minus 9.81 meters per second squared. Gravity is going to accelerate the ball towards the ground. Will the ball get any higher than 230 meters? Do we have to calculate anything at all? We want the maximum height, ignoring air resistance. As the ball comes out here, first you should realize that this 5 meters per second has absolutely nothing to do with the problem. It's in a direction perpendicular to the vertical direction. We want height. We never use any numbers that are not in the direction of the height when we want to calculate a height. So completely ignore the 5 meters per second. The ball does possess 22 meters per second of upward velocity as it goes out the door. This 5 meters per second does not take away the motion the ball had before it rolled out the door, 22 meters per second. So the ball is moving upward. It's going to go up a little bit, and represented here, it'll go up a little bit, and then it's going to come back to the ground. So we want to know what the maximum height is above the ground. We're interested in, at the top of the motion, how far are we above the ground? And also I should point out there won't be any danger of hitting the blades of the helicopter. As the helicopter moves upward, the ball is moving upward at the same speed, but the acceleration is negative, so the ball's upward speed is going to decrease until the speed is 0 at the top of the motion. So at the top of the motion, the ball has 0 meters per second. We can say that. We do not know the time to get up to this high point, so we don't know that. How could we use a kinematic equation to help us out here? We do know the original, the V naught for the ball is 22 meters per second. It shared that helicopter motion before it rolled out of the doorway. So we know the initial speed, we know the final speed, we know the acceleration. We want to calculate how high the ball goes. Well, there's a kinematic equation for that. The final velocity squared is the initial velocity squared, plus 2 times a, the acceleration, and times this distance until we get to this place where the final velocity is. And that's going to be the height that we want. Because final velocity is 0, our initial is 22. I won't bother writing the meters per second. And then 2 and minus 9.81 meters per second squared. And y, it's straightforward. There's no substitution needed or quadratic formula, so forth. You should use your calculator and confirm that y is 24.7 meters. Is this the height above the ground? No. This is the height above the release point, if you will. It's when the ball separated itself from the helicopter. That's y equals 0 in this calculation. I'll go ahead and put it there. Y naught equals 0, right where the ball comes out of the helicopter. And we go up 24.7 meters from there. That's the place where the velocity is 0. So maximum height for the ball above the ground will equal 230 meters. That's where this motion started, plus 24.7 meters. So we're up at 254.7 meters. That's the maximum height of the ball. You could round that to 255 meters if you'd prefer. Okay, second part of the calculation, what's the total time from when the ball goes out the door till the ball hits the ground? And again, we're going to ignore air resistance. It's too complicated for introductory physics to calculate that. Well, there's a couple different ways. If I have room on the paper, I'll do both methods here. We want the time for the ball to hit the ground. The first way is I'm going to separate the motion into two parts. This total time to hit the ground is equal to the time for the ball to go up to the top of the motion, and then the time to come back down. So the time to go up and the time to come back down. To do the time going up, I'm going to use this kinematic equation, v equals v naught plus at. At the top of the motion, the velocity is 0. We started at 22 meters per second. The acceleration is minus 9.81 meters per second squared. And time to go up. So it's a direct calculation again. Add this term to both sides and then divide the 22 by 9.81. And the time to go up, I'm going to write it here because I know I'm going to need some extra space. The time to go up is 2.24 seconds. How about the time to go down? Okay, on the down, we do not know the velocity as the ball is about to hit the ground. Sorry, I'm continuing to run out of video space here. We don't know the final velocity, just the instant before the ball hits the ground. So what do we do know? We do know the maximum height, 254.7. We know the distance that the ball is going to travel. So I can use this equation. Very often this is the third equation in the list of the kinematic equations. You should recognize it. The distance traveled, initial velocity multiplied by t plus 1/2 at squared. And again, everything here is in the vertical direction. The y, the v naught, the a, all those are vertical numbers. So as I put those in, I do need to consider where y is equal to 0. And I'm going to let y equal 0 at the ground. And the y that the ball travels is a negative. It's going down to the ground. Maybe I should do this differently. At the top. Let's make this at the top. A little change in gears. I'm going to let y equal 0 at the top. I need a negative over here. So minus 254.7 meters equals, well, at the top we started with 0 velocity, and 1/2 minus 9.81 and t squared. So again, pretty direct calculation. The minus signs will cancel. So take the 254.7, multiply by 2, divide by 9.81, and I get a t squared of 51.93. But I have to remember to take a square root, and I get a time coming down of 7.21 seconds. And the time to hit the ground then is the addition of the time to go up after coming out the helicopter. That was 2.24 seconds. Plus the 7.21 seconds of going from the very highest point down to the ground. We found that using this third equation. So you can see my work now. So the time to come down after the ball goes out the helicopter until the ball hits the ground is going to be 9.45 seconds. So that's one way to work the problem. Now I have enough space on my paper here. I'm going to work this a different way. The second way is to do the calculation starting when the ball leaves the helicopter until the time it hits the ground. And now I am going to let y equals 0 at the ground. So and I think I'll take that back again. Y equals 0 at the top. So anyway, so this y, the distance traveled, is minus 230. That's where the ball came out the helicopter. The helicopter was 230 meters above the ground at time equals 0, where I'm starting this calculation. And then we've got 22 meters per second multiplied by the time in the air, and then plus 1/2 minus 9.81 t squared. In rearranging this, getting into more standard quadratic form, so 9.81 divided by 2, and then this negative term I'm going to add to both sides. So I get a quadratic that looks like this: 4.905 t squared minus 22t. This term has been subtracted from both sides. Minus 230 equals 0. Quadratic equation. So we solve that with quadratic formula. T equals minus b plus or minus square root of b squared minus 4ac, all divided by 2a. The a is 4.905, b is minus 22, c is minus 230. It's important to keep those minus signs with b and c. So when we do that, the b squared minus 4ac, and take a square root, that turns out to be 70.7. The minus 22 creates 22. Plus or minus, after I do the square root, 70.7. You ought to confirm that with your own calculator. And then 9.81 for 2 times a. If I use the plus sign to do this calculation, I come up with a t-value of 9.45 seconds. Does that look familiar? Well, yeah, back here is the method of doing the calculation with separate pieces going up and then coming down. Here, using quadratic formula with this third equation, starting from when the ball comes out the helicopter door, and the ball is in this time in the air, the ball is going to drop 230 meters getting down to the ground. Again, I'm working up to be the positive direction, and that causes this y number here to be a negative. The ball's moving down to the ground. That's a minus 230 meters. When the y equals 0 is at the door of the helicopter when the ball came out. Ball is moving upward, so that's a plus for the v naught. The acceleration of gravity is a negative, so that's a negative for the a value in the at squared. Work it through, get into standard quadratic form, work it into the quadratic formula, and I'm not even going to bother to calculate with the minus sign. That's a negative time. That's not physical for this problem. 9.45 seconds. So sorry about the double takes on defining y equals 0 at the top rather than at the ground. You ought to convince yourself that y equals 0 at the top is the better choice, the way I'm setting up the positive and negative directions. And hope this is a understandable example for you. Keep practicing on your own.